So before we look at percent composition, let's look at percent by mass in a general manner. And make sure my pen is working here. So percent mass equals, in general, the mass of a part divided by the mass of the whole times 100. For example, 2.4 grams of carbon dioxide are found in 300 grams of carbonated water. Just gonna make that H2O. What is the percent CO2 in the sample? The part is the mass of the CO2. So percent CO2, and this is by mass, equals 2.4 grams CO2 divided by 300.0 grams of the carbonated water, or the sample, the whole. Okay, so doing that math, we get 0.80%. Now I have two sig figs here, and that's because of the mass of CO2 in this calculation. It has only two significant figures. We're dividing, so it's least number of sig figs, so I need 2 in my final answer. I will frequently try to include sig fig discussion during these calculations. So now let's look at percent composition. So this is the mass of an element, and we're looking at the element in a compound, divided by the molar mass of the compound. So we're going to look at the example on this slide, which is, and I'll explain, this is number of moles. And again, we're using molar mass, which has units of grams per mole. Okay. So we are going to calculate the mass of each element, and when we do that, we need to use its subscript, which tells us how many moles of that element are present in the compound, and the molar mass. We also need to calculate the molar mass of the compound, and that is 46.07 grams. So we'll divide the mass of carbon by the mass of the 1 mole of the compound, multiply by 100, and carbon is 52.14%. We do the same thing for hydrogen. There are 6 moles of hydrogen in this molecule. So we multiply the molar mass of hydrogen by 6 and divide by the mass or molar mass of the compound to determine the percent hydrogen. And finally, the same calculation for oxygen. Now, in an ideal world, when we add up those percents, they should equal 100. Now, if we're working with experimental data, we might not get percents that equal 100 exactly. It might be a tenth or 100th off, plus or minus 100, but it should be very, very close to that 100%. So if you are doing these calculations and you get a percent that's total percent that's like 80%, then you've made an error somewhere. Or if you have a percent of 110, you've also made an error in your calculations. So think about your answers before you finally submit them. So we are going to then use percent composition to determine what we call an empirical formula. So let's review empirical formulas again. So empirical formulas, or the simplest formula, gives the smallest whole number ratio. In those subscripts of the formula versus the molecular formula, so this would be for a covalent compound. This represents the actual number. Represents of each type of atom in the compound. Okay? The molecular formula is always going to be a multiple of the molecular formula. So let's look at some examples. Molecular versus empirical. C2H4. This is an organic compound or molecule covalently bonded, and the subscripts on each of those elements can be divided by 2. So this is not the simplest whole number ratio. The empirical formula is CH2, and I might add that there are some molecular formulas that cannot be, the subscripts cannot be divided to get whole numbers. So both their empirical and molecular formulas will be the same, and I'll give you an example of that as well. H2O2, this is hydrogen peroxide. Empirical formula is HO. N2O4. Empirical formula is NO2. Molecular nitrogen, simply N. And lastly, looking at water, we see that the subscripts cannot be divided by 2 to get whole number ratios between those elements in the compound. So in the case of water, the molecular formula and the empirical formula are the same. So we can use mass spec data to determine empirical formulas of unknown compounds. But prior to running through this, I want to point out that what kind of information we need to determine an empirical formula. We need all the elements that are present in the compound, and the percent by mass, or mass relationship for the elements that are present. So we can use mass spec data, the mass percent from a mass analysis, and we can convert that to grams and divide by molar mass to determine the number of moles of each type of element in that compound. We then divide by the smallest number of moles to come up with a mole ratio between those elements. And then, if need be, we change to integer subscripts to get that empirical formula. And we're going to walk through an example of that, and then we'll do some problems on our own. So we have analyzed a compound and found the percent composition by mass. It contains potassium, manganese, and oxygen, and their relative percents. For each of these percents, we can assume (100 grams) of the compound. And if we have 100 grams of that compound, then we can say that of that 100 grams, 24.75 grams is potassium. Then we use the molar mass to convert those grams to moles. And we do that for each element in the compound. So grams cancel and we're left with moles. We do the same thing for manganese, convert that percent to grams because we assume 100 gram sample. So we get the number of moles for each of our compounds, or elements within that compound. We have we are going to here we go. There we go. We look at the number of moles for each element. Forgot I needed to switch that slide. And we identify the smallest number of moles. And that's 0.6329. Not a big difference between potassium and manganese, but there is. So that's the smallest number of moles. So now we're going to set up the mole ratio using that smallest number of moles for each element and divide. And we get whole numbers. Some manganese is an exact 1.0, and potassium and oxygen are very, very approximate to, are very, very close to a whole number. And if we are that close, then we assume that that is the whole number. I'll give you an example of what we do if that isn't the case. So our molecular formula for this compound is KMnO4. All right, so let's practice some of these ourselves. So we're going to start with one that's relatively simple, and I'm going to show you how we can determine also the molecular mass of the compound, or not the molecular mass, the molecular formula. Sorry about that. So we are going to find the empirical formula for a hydrocarbon. What is a hydrocarbon? This is an organic compound that contains only carbon and hydrogen. And sample analysis gave us 85% or 85.63% carbon and 14.37% hydrogen. Now we're going to come up with the empirical formula, and then with some additional information, we will determine the molecular formula. We are, again, going to assume we have 100 grams of our sample. So that means we can convert our percent directly to grams. So we have 85.63 grams of carbon, and we'll find the molar mass on the periodic table, and that is 12.01 grams for 1 mole of carbon. So the moles of carbon are 7.130 for sig figs. We'll do the same calculation for the hydrogen, 14.37 grams of hydrogen. Use the molar mass of hydrogen. And convert that to moles. We have 14.26 moles of hydrogen. So our ratio, this is the smallest number of moles. Ratio set up is this, and that gives, well, this is 1, obviously, and this is 2. So our empirical formula is CH2. Now, we also determined through analysis the molecular mass of that compound. And it was 112, I should say molar mass, grams. Using that, we can determine the molecular formula. And all we do, again, is set up a ratio. But we use the molar mass of the empirical formula. So this is, we only have 1 mole of carbon. And here we're setting up a ratio, so we don't have to use, all the decimal places here. 1 mole of carbon, so we have 12 plus 2 times 1 for hydrogen. And this equals 14. So our compound has a molar mass of 112 grams, or our sample. So we take that 112, divide it by 14, and we get 8. So this is the multiplier. Whoops. For our empirical formula. So remember, the molecular formula in most cases is a multiple of the empirical formula. So we take C, which we have 1, multiply that by 8, And for H, we had 2. Multiply that by 8. Our molecular formula then is C8H16. We'll do one more. This one is a little more complicated. And we're going to use vitamin C. And vitamin C contains carbon, hydrogen, and oxygen. It's an organic compound. And we analyzed a sample with a mass of 1.00 grams. And we found that of that 1.00 gram, 0.409 grams were carbon, and 0.0458 grams came from hydrogen. And we're asked to determine the simplest formula which, again, is the empirical formula. So we have the masses of carbon and hydrogen, but we don't have the mass of oxygen. So we need that mass as well, and then we will convert our masses to moles, find our mole ratios, and come up with our empirical formula. So we know that we have a 1.000 gram sample, and we have the masses of carbon and hydrogen. So we're just going to subtract those from the total mass of that sample. To get our mass of oxygen. So now, find the moles of each element in the sample. Using the mass of that sample, or the mass of that element, sorry, and the molar mass of that element. So we have 0.0341 moles of carbon. Do the same calculation for hydrogen and oxygen. Oops, sorry. Moles, not grams. And finally, moles of oxygen. And in looking at our moles of each element, we see that moles of O and moles of C are the same, and they are the smallest number of moles. So that is what we're going to use to set up our ratios. So for carbon, 0.0341. For hydrogen, 0.0454 and oxygen. Now, when we divide these, the ratios come to 1, 1.33, and 1. 1.33 is not close enough to 1 to be considered 1. So we are going to have to find a multiplier to make a whole number. And we need to multiply this by 3. But we don't just multiply that ratio product or result. We have to multiply all 3 of them. So for carbon, we have 1 times 3. For hydrogen, we have 1.33 times 3. And for oxygen, 1 times 3. So our empirical formula, or our simplest formula, is C3H4O3. That's it for percent composition and empirical formulas.